Okay, in this problem, we need to calculate the cutoff frequency and then determine if this is actually a high-pass filter or not. So here's my V in. I have a capacitor and a resistor, and this is 1.5 kiloohms. I'm measuring V out here. Right, so this just looks like a voltage divider. And this is 0.1 microfarad. Okay, so we need to find FC, the XC, Z, and then V out for V out. Let's see, V out for V out at cutoff, and then low F and high F. Okay, so let's start by calculating the cutoff frequency. This is going to be 2 pi RC. And over that, so FC is equal to 2 pi times 1500 ohms times 0.1 e to the minus 6 farads. And so when we plug that in, we get 1061 hertz. So that's our cutoff frequency. So now the next thing we want to do is find the let's find the output. Let's find V out at cutoff. And so that's going to equal V in, I think, yeah, V in, times R over Z, which is equal to V in times R over R squared plus XC squared, square root. But at FC, we know that R is equal to XC. So we're going to add that to our equation. At cutoff is going to be V in, and then XC over XC squared plus XC squared square root, which is equal to V in, and XC over, we factor XC out of both terms on the bottom. So, and then we can bring that outside. And then this is just going to be the square root of 2. So V out at cutoff is equal to V in over the square root of 2, which is equal to 0.707 V in, which is what we'd expect for at the cutoff frequency, that is the output that we would expect. So now let's look at a low frequency. So low frequency, we want to find XC. So XC is equal to 2 pi FC. And so XC is equal to 2 pi. And we're going to say low frequency is 100 hertz. Right? If cutoff is 1,000, then low frequency is 100. That seems pretty good. So 100 hertz times 0.1 e to the minus 6 farads. So XC is equal to 15,915 ohms. And now if we want to find the Z value, this is going to equal R squared plus XC squared. So Z is equal to 1500 squared plus 15,915 squared. And so Z is going to equal 15,986 ohms. And so V low, V out low, do that, is equal to V in, and now I'm measuring across my resistor. So I'm measuring from here to here to ground. So this is my V out, is in between the elements, in between the two components, and I'm measuring the output with respect to ground, which is just the output of the voltage across that 1.5 ohm resistor. So that is just my R over Z, right, which is V in, and R over my Z in this case is, so let's hold on a second, let's erase that, and I'll plug in my R value. My value is 1500 over 15,986, and this is equal to 0.09 V in. So it does not pass low voltages, low frequencies. Now let's check the high pass. So high pass meaning I'm passing high frequencies. So high frequencies, we're going to say that high frequency is 2000 hertz. So XC at 2000 hertz is going to be 1 over 2 pi FC, which is 2 pi times 2000 hertz times 0.1 times 10 to the minus 6 farads. And so XC is equal to 796 ohms. Z high frequency equal to R squared plus XC squared square root is equal to 1500 squared plus 796 squared square root. So Z high is equal to 1698 ohms. So to find the output voltage, again, I'm finding the output voltage across the resistor. So V out high equal to V in times the ratio of the resistance to Z. And so I'm going to have V in, and R is 1500. And Z for high frequencies is 1698. So this is going to be V in, and I get 0.88. And so this is definitely passing high frequencies. So I would say this is a high pass filter. And it means that by measuring the output, the voltage across the resistor, most of the input signal is output for high frequencies.